In this lecture, we'll examine factors which influence high-intensity sprinting performance and look at a few examples of fatigue or mechanisms of fatigue during this type of exercise. So if we think about a high-intensity effort that might go for 10 seconds through to 40 seconds, 100 metres, a 200 metres or a 400 metre event, really intense efforts where ATP needs to be generated very quickly and the byproducts of that intense exercise need to be tolerated and managed. If we look at the general characteristics of sprinters, we see they have a high muscle mass and a very well-developed ability to generate force and power. They often have lots of fast twitch fibres. I may have made the comment that sprinters are born and marathoners are made. The ability to recruit those muscles, they've trained their nervous system to rapidly recruit those active muscles. And even in these shorter events, they need to manage fatigue. How often have you watched a 400 metre race and seen particular runners really fatigue in the last 50 to 100 metres? The ability to generate and tolerate metabolic acid, and this is related to the buffer capacity, and of course, a fast reaction time. The excitability of the muscle membrane is very much determined by the balance of potassium and sodium across the sarcolemma. And one of the major changes that occurs during very intense exercise is a large increase in extracellular potassium. And you can see here from this graph the change in femoral arterial and venous potassium levels with a very intense sprinting effort. You can see very high levels. Of course, this is very rapidly reversed in the recovery period. And where attempts have been made to measure potassium in the interstitial space, right near the sarcolemma and the T-tubule, even higher values have been recorded. And these large increases in extracellular potassium really do impact on the excitability of the membrane. So effects and responses that affect the sodium-potassium pump and the ability to resist the changes in sarcolemmal excitability with these big changes in potassium are important for high-intensity exercise. And here, if we just go back again and look at the fuels for high-intensity exercise, you can see here in this study where ATP, phosphocreatine and glycogen were measured in single fibres, both type 1 and type 2 fibres, before and after a very intense treadmill sprinting bout. You can see, particularly in the type 2 fibres, a very large reduction in the levels of phosphocreatine and a slight reduction in the ATP levels. And so the availability of fuels may also be very important during this type of exercise. And as I said in the last lecture, the localized reductions in ATP may be very critical, even though it may be difficult for investigators to see those declines when they measure at even the single fibre or the whole muscle level. But to show you some of the changes that might occur, this is the same graph that you saw in one of the early lectures on fuels for exercise. Well, if you repeat that exercise, that 30-second exercise, on a second and a third occasion, here is the response and the contribution of those energy systems during the third bout. And you can see that there's a marked reduction in ATP turnover consistent with the lower power output. And a lot of that is due to a reduction in the contribution from phosphocreatine, a small contribution from anaerobic glycolysis, and although the relative contribution of oxidative phosphorylation is higher, it still is not able to sustain a high power output. One strategy that's been utilised to try and improve fatigue resistance during these repeated bouts of exercise is dietary creatine supplementation. And you can see here in bout 1 and bout 2, the total work that was generated during these 30-second bouts before and after a period of dietary creatine supplementation. And increasing creatine availability is associated with an increase in phosphocreatine availability and a greater contribution from that energy system to power output. And as a result, more work is achieved during those bouts. And you can see, even though there's still fatigue, there's a higher work output with the creatine supplementation. Now, there's lots going on during repeated bouts of high-intensity exercise. There's depletion of of energy substrates, phosphocreatine and glycogen. There's increase in hydrogen ion, and there's also changes in SR function. And one study that we undertook a number of years ago was to look at these repeated bouts of exercise. And so we had subjects do 3 high-intensity efforts, 30-second all-out efforts, separated by about 3 to 4 minutes. And then we had them rest for an hour or so, and then they did a 4th bout. And you can see, if you look up here, that the power and the work output decreased over those 3 bouts. And while it came back a little bit, there was not complete recovery, but a substantial amount of recovery during the 4th bout. We then looked at ATP, creatine phosphate, and glycogen levels in the muscle, and you can see that the creatine phosphate levels had certainly returned in the 4th bout. The glycogen was still reduced somewhat. The hydrogen ion had gone down. The ATP was still down a little bit, but not too much. And the SR calcium uptake, our measure of SR function, had recovered. So the 4th bout, we'd normalised hydrogen ion, we'd normalised creatine phosphate, the glycogen was still low, and the performance, you can see, was affected a little bit. So that gave us some insight as to what factors might be important. And perhaps the availability of glycogen was, per se, was less important in this context, and maybe some of the other changes were more important. There's been a lot of debate in the literature about the role of hydrogen ions. For many years, lactic acidosis was seen as the real enemy of the sprint athlete. And indeed, there are lots of effects associated with the metabolic acidosis. But the ability to produce large amounts of lactic acid means that energy is being generated from glycolysis at a high rate. Remember the relationship between power and capacity. So if you want to generate ATP very quickly, then anaerobic glycolysis is the system you want to activate. As I said, for many years, an increase in hydrogen ions was seen as a negative factor in force production. There were some studies then in isolated muscle which cast doubt on whether a low pH or an increase in hydrogen ion concentration was really a cause of fatigue. It's difficult to study this in an intact human model, but this is a rather elegant study looking at the recovery of both maximal voluntary contraction, or the maximal force output during an isometric contraction, and the ability to maintain that contraction at about 2/3 of your maximum. So this is really the maximal force, and here is your endurance. And this was done after a very intense fatiguing contraction, and you can see that the ability to generate force recovers very quickly, even though there's still a lot of hydrogen ion in the muscle. The ability to maintain a contraction, however, takes quite some time to recover, and even after 40 minutes, it's still not quite back to the pre-fatiguing level. So this implies that perhaps something about acidosis or hydrogen ion availability might impact the ability to maintain a muscle contraction rather than just generating force per se. The other studies that have been done to investigate the potential role of acidosis involve the ingestion of agents that increase the pH of extracellular fluids, in this case bicarbonate. You can see in this study where subjects undertook repeated bouts of high intensity exercise, the muscle pH was measured. You can see at the start of the final exercise bout, the muscle pH was higher with bicarbonate than with the control sodium chloride experiment. And this, it's known that increasing the pH of the extracellular fluid facilitates the efflux of hydrogen ions, possibly some lactate, from contracting muscle. And this might have contributed, at least in part, to the improved exercise tolerance. It's also been shown recently that acidosis and alkalosis can have effects on the sodium-potassium pump. And so maybe there's another explanation unrelated to the any direct effects of hydrogen ion on excitation-contraction coupling, but maybe it's related to excitability. One interesting aspect in relation to managing acid-base balance during high-intensity exercise is to look at what happens with sprint training. And here is one of the first studies to look at a biomarker known as the muscle buffer capacity. And this can be estimated either in vitro by taking muscle and putting it in a test tube and titrating it with acid and looking at the pH change, or you can estimate that in vivo by looking at the relative changes in muscle pH and muscle lactate, at least as a marker of glycolytic rate. And you can see here, this was a period or measurements made before and after high intensity sprint training, and this is the buffer capacity, and you can see that it's increased following the sprint training. And for comparison, the authors of this study also studied a group of endurance trained athletes, and you can see that these endurance trained athletes didn't have that adaptation to sprint training. One interesting aspect of this is some of the buffers in muscle. There are proteins that are buffers in skeletal muscle, and there's a dipeptide known as carnosine, which is known to have important buffering effects. One of the precursors of carnosine is a compound called beta-alanine. And in recent years, there's been interest in beta-alanine, dietary beta-alanine supplementation as a strategy to increase muscle carnosine and increase high-intensity exercise performance. And you can see from this study, that's exactly what we've seen. A parallel design with a group of subjects who received carnosine and a matched group that received a placebo. And you can see that the experimental group that received beta-alanine increased their muscle carnosine, and that was associated with a slight but significant increase in their high-intensity exercise performance. No such changes in the control group. So increasing the ability of skeletal muscle to buffer changes in pH during high-intensity exercise appear to be associated, at least, with improved exercise performance. And so if we look at the adaptations to sprint training, and that might give us some clue as to some of the important characteristics of sprinters that contribute to their success or the improved performance following sprint training. As I said, one of the adaptations that you see is an increase in the sodium-potassium ATPase activity, or the sodium-potassium pump, and that's associated with improved potassium regulation. An increase in muscle buffer capacity, as well as an enhanced capacity to exchange or to transport lactate and hydrogen ion. Not all of the buffering of acid in muscle occurs with interactions of fixed buffers. Some of the transport mechanisms that export hydrogen ion from muscle, and other electrolytes for that matter, impact very much on acid-base and electrolyte balance. There's increased glycolytic enzymes. Many of the key enzymes in glycolysis are increased following sprint training. And an observation made intermittently, but more so in recent times with the interest in high-intensity exercise training, increases in VO2 max and muscle oxidative capacity. And these are probably associated with the significant activation of the cardiovascular system, an increase in cardiac output during very intense exercise, which will stimulate some of the cardiac adaptations we saw in one of our earlier lectures, as well as activating some of those signaling pathways which turn on mitochondrial biogenesis within skeletal muscle. And finally, I'll come back to that old adage that sprinters are born and marathoners are made. There's no really good evidence that sprint training can suddenly increase the proportion of fast twitch fibers in skeletal muscle. In contrast, endurance training can certainly increase the oxidative capacity of the fast twitch fibers. So, as I said, there's no good evidence that sprint training will have a major impact on fiber type composition.